Good afternoon, everyone.
Yes, that's a good point.
Welcome to the first colloquium of 2014. And today we are honored to have Professor Jan-Willem van Holten as a guest of today's colloquium. Before I start introducing him, actually, I would like to make two announcements. That he will be here tomorrow, and he will be giving two seminars or two talks. One for honor, chemistry honor students at the chemistry department at 8:30 in the morning. So I'd like to encourage our undergraduates also to attend this talk. The second lecture he will be giving is Hugo Rossi Center of Science and Math Education lectures, and he's going to talk about a project which or an experiment which they are doing in the Netherlands with cosmic rays detectors in high schools. So the talk will be at noon at the INSCC room 1110. So Professor Van Holten actually he got his PhD in Leiden University in the 1980s, and he was working on construction of supergravity theories. Then later he did a postdoc at CERN and also at the University of Wuppertal in Germany. And currently he's a staff member at the Dutch National Institute for High Energy Physics and Subatomic, and also a professor of theoretical physics at Leiden University. So today his research interests include gravity, supersymmetry, quantum field theory, and today he will be talking about some of the projects he is involved in. And the title of his talk is Listening to Universe, Gravitational Waves and Their Sources.
Okay, Tino, thank you. But Tino forgot to mention that he was a PhD student with me in Amsterdam. So the subject of my talk is gravitational waves. And gravitational waves, as I will explain in more detail later, are a prediction of Einstein's theory of general relativity, which is now almost 100 years old. And this theory, when it was first invented, Einstein used it to make a number of predictions, or at least calculations which were confirmed by experimental observations. First one was well known, the shift of the perihelion of Mercury, very small effect which had been measured already in the 19th century and which came out of the theory of general relativity with unexpected accuracy. Second was the bending of light by gravitational fields like those of the sun. And the third one, the redshift of photons in the gravitational field, or light in the gravitational field, because the concept of photon was kind of in the statu nascendi at the time. But the theory of general relativity, in addition to predicting some new effects of this type and explaining some aberrations of Newtonian physics, general relativity also made a number of more fundamental predictions, and two of them in particular are very relevant for our understanding of the universe. The first is the prediction of the existence of black holes, and the second one, the existence of gravitational radiation or gravitational waves, similar to the existence of electromagnetic waves in Maxwell's theory. And so those two predictions actually have been inspiration for many researchers ever since. And today I will actually try to explain to you how one of these predictions can be maybe used to test the other one. So, but before doing that, maybe I should just briefly review for you the aspects of gravity which are peculiar to general relativity. Gravity theories, already the first one which was actually formulated by Newton in the 17th century, make use of some very peculiar idea called the equivalence principle. It was known already long before Newton that objects in a gravitational field fall at the same accelerating rate independent of their mass. And it's well known that, or there is a story that Galileo actually did an experiment where he dropped cannonballs from the tower in Pisa and discovered that they reached the ground exactly at the same time, even though the one was 10 times heavier than the other one. Now this story has some truth in it, but it's actually, the details are different. Galileo described this experiment in one of his dialogues as a thought experiment, but the experiment was carried out 25 years earlier, I should say in the Netherlands, by another physicist of the time known as Simon Stevin, or Stevinus maybe, who was an expert in mechanics and especially in statics and hydrostatics. And he and a colleague, they did this experiment from the church tower in Dordrecht, and they actually published the result in one of the books that Stephen wrote, which was called Principles of Weighing, of Weight. And Galileo probably knew this book and the story and used it to illustrate some of the arguments in his dialogues. So two objects with different mass fall at the same rate in gravitational field, and that is actually because the gravitational force on an object is proportional to its mass. But as you know, acceleration is equal to force divided by mass, and therefore the acceleration due to gravity is independent of the mass. And that's why objects with different mass have the same gravitational acceleration. Now, a direct consequence of that is that if two objects very close together are falling in free fall in a gravitational field, they are not accelerated with respect to each other. Right? They fall at the same acceleration. So one, they see the same. If they start at the same time, they see each other fall together. Or if one is already moving a little bit earlier, there will be a relative velocity, but there will be no relative acceleration between the two objects. So that means that if you are in free fall and you see all the other objects around you fall also freely, all these other objects are not accelerated with respect to you. That means that your observation system, your coordinate system that is attached to you, is actually an inertial system, because inertial systems are defined as systems in which all free particles are either at rest or move at constant velocity. And that's what the case if you are in free fall. So that means that actually free falling objects define local inertial frames. And Einstein actually had the fantastic idea that this meant that you could base space-time geometry on the creation of, by gluing together coordinate systems that belong to local inertial fields. So you are in free fall, you can construct a coordinate system in your neighborhood. Somebody else a little bit further away is in free fall, constructs a local inertial frame in his neighborhood. And by gluing all these local inertial frames together, you get a coordinate system for all of space and time. And that coordinate system for all of space and time, the global coordinate system, doesn't have to be a flat represent a flat geometry. It can represent a curved space geometry. That means that if you are falling from one or moving from one point in space-time to another point, even if you try to minimize the time or the distance between those 2 points in space and time, and locally that means that you are moving on a straight line. Globally, this means that you are actually moving on a curve if there is non-trivial gravitational force. So the idea is that gravity and geometry are closely linked to each other, and that gravity is in fact a manifestation of non-trivial geometry of space and time. Now, not only is gravity can gravity be thought of as curvature of space and time, so that bodies that move in the gravitational field actually move in a curved space and time, and therefore not along straight lines, and so they can be accelerated, because if you have two objects moving in this curved space, then of course these two curves will not be parallel everywhere. So that means that if you move each in your own free fall system, you do actually see the other object accelerated with respect to you, because the curve, the geometry is slightly different here than it is there due to curvature. So curvature is really what is causing gravitational interactions. And now the principle on which Einstein built his geometrical theory of gravity is that mass is a source of curvature. Mass tends, or energy, tends to curve space-time around it, and that other bodies moving in this curved space then of course move on space-time geodesics, which are not straight lines, but are curved world lines. And this is the geometrical interpretation of gravity. So curvature is the source of gravity, but curvature is not static, it's a dynamical thing. It can change because masses can move around. And so the curvature is not fixed for forever once you have some distribution of objects in space and time. And the equation that Einstein wrote down for the geometry of space and time, this famous Einstein equation, tells you basically that this object, r mu nu, which in some way represents the curvature of space-time, is actually caused by the distribution of matter, or energy and matter in space and time, represented by this object here called the energy momentum tensor. Now the constant of proportionality, which would be something like, say, the epsilon zero in electrodynamics, is actually Newton's constant, and it's extremely small number, and that means that gravitational curvature in general is very difficult to create. However, even at the qualitative level, it's clear that once gravity and geometry of space-time become something dynamical, you can change curvature here by moving a mass. This change in curvature can start to propagate throughout space and travel to other places. So you can create ripples in the geometry of space and time. And these ripples is what we interpret as gravitational waves, just like we interpret small perturbations of electric and magnetic fields that travel through space and time because of the motion of charges and currents as electromagnetic waves. Now, in particular, if you look for small deviations from flat space geometry around Minkowski space, then you can actually write a linearized version of Einstein's equations, and you find that these disturbances, they are represented by this object h mu nu, can propagate through space at the speed of light, or that's what they do, and that they have in fact always two possible polarization modes, which are transverse to the direction of motion, just in the same way that electromagnetic waves propagate through space, and they have two transverse polarization states. It can be linear polarized in the transverse directions, or they can have circular polarizations, left-handed and right-handed, with respect to the direction of motion. Now the same is true for these gravitational ripples, and here you see them illustrated. If you have a collection of test masses which are at rest on a circular in a circular configuration, and a gravitational wave hits this configuration in a perpendicular direction, so from say perpendicular to the projection screen here, then this circular distribution of masses will start to oscillate, not in a linear fashion like in electromagnetic waves, but in this special way where one direction is squeezed and the other is elongated, and half a period later it's the other way around. And the two polarization modes correspond basically to two of such oscillations which are rotated with respect to each other by 45 degrees. These are the two polarization states that we associate with gravitational waves, and they're called quadrupole polarizations, so quadrupole modes. If you construct a quantum theory of quanta of these gravitational waves, just like you would do for photons in the case of electromagnetic waves, then photons, which are circularly polarized, represent states of spin 1, and these gravitational waves will actually represent waves of spin 2. So gravity can be thought of, at least this small amplitude gravity effects can be understood as massless spin 2 particles propagating through space and time. And actually, you can show that the coordinate system can always be chosen in such a way that there are only two components of this object h mu nu which are non-zero, representing an xx and x and yy mode and an xyy mode, and they satisfy the wave equation, the massless wave equation.
Question?
Yeah.
Is there experimental evidence that the gravity waves propagate at the speed of light?
Not that they propagate at the speed of light. That is still something to be tested. But I will come to experimental observations later in my talk. So let me first explain to you why it's so difficult to test this prediction of general relativity. It's difficult because although space is dynamical and the geometry of space is something that can be changed, nevertheless it's very difficult because space is extremely stiff. And you can see that in this plot here. Here I have plotted the amplitude of a gravitational wave against the frequency for various intensities. And the intensity of a gravitational wave is just like in the case of electromagnetic waves. It's just made by taking the square of the amplitude and multiplying with appropriate Newton's constant, well, 1 over Newton's constant. And then you can calculate the energy flux associated with these gravitational waves. And because Newton's constant is so small, the flux has to be very large to create very small amplitudes. This amplitude h you can think of basically as the relative deformation of an object. So suppose that a gravitational wave is passing by, then everything in the path of the gravitational wave gets squeezed and elongated periodically. Now the amount by which it gets squeezed, the relative amount, is the change delta x over x, is what is actually coded by this amplitude h. That means that if, say, h is 10 to the minus 20, which is here on this plot, it means that an object of 1 yard in length will be squeezed by a factor of 10 to the minus 20 yards, which is less than the diameter of a proton. Far less than the diameter of a proton. So that's why it's so hard to observe gravitational waves, because the effects are so extremely small. You see that, in fact, if you want to have an amplitude of 10 to the minus 20 at the frequency of 1 kilohertz, you have to have fluxes, energy flux of gravitational waves of watts per square meter. That's enormous, given the smallness of Newton's constant. So that basically means you only can expect to observe gravitational wave from huge masses in astrophysical systems. Say neutron stars, black holes, or things like that. They give you enough deformation of space and time that actually you may hope to observe some of these small effects on the surface of the Earth. And as we will see later, the actual experiments going on at the moment, terrestrial gravitational wave detectors, they are all acting in the frequency range above 20 hertz, so between 20 hertz and say 1 kilohertz. And in that frequency range, they have reached sensitivities of at least 10 to the minus 22. And still, at the moment, no direct observation of gravitational waves has been made, unfortunately.
Excuse me?
Yeah.
What's the mean free path of this wave? Is it known?
The mean free path is essentially equal to the radius of the observable universe, because the flip side of the fact that space is so stiff also means that gravitational waves lose very little energy when they scatter from anything. In fact, most of the gravitational waves pass right by any distribution of mass in the universe without being deflected, and only very tiny fraction of the waves will ever be absorbed by any system. That's another reason why it's so difficult to observe these gravitational waves. There is really not enough matter density in the universe to absorb these gravitational waves in a really
There should be
large
enough.
amount.
If we get some gravitational waves.
If they would be coherent, coherent, but there are no standing waves, so to speak. That would be very nice. If you could invent some way to make a laser, a gravitational laser, that would be fantastic. So let me try to estimate a little bit the strength of some astrophysical sources. And as long as you have masses which are moving non-relativistically at speeds very small compared to the speed of light, essentially the source of gravitational wave is the time dependence of the quadrupole moment of the mass distribution, and that is this object here. Rho is the mass density, and r is the position of the various mass elements in the distribution. And this object is a traceless object here, is called the quadrupole moment. If you compute it, you take the third derivative with respect to time and squared, you get the power emitted in gravitational waves. And it's easy to evaluate this formula for binary system. Suppose you have two masses, like say the Earth and the Sun, or any other system of two masses which are moving around each other. Then the power, according to this formula in gravitational waves, is given by the fourth power of Newton's constant divided by the fifth power of the velocity of light, the fifth power of the radius of the system, and then here you have the total mass, capital M, and the reduced mass, which is the product of the two masses divided by capital M, which I call mu. And in this plot here, you see basically quantitatively what this implies. There are two curves here. First, the blue line here actually represents the frequency of, or the period, the frequency of the motion of this binary object. Because if you have a circular orbit, two masses in a circular orbit, then the period at which they rotate around each other is basically determined by the radius, the distance between the masses. So it's easy to plot the period as a function of radius, or the frequency, which is the inverse, and you see that here if you have a distance of one astronomical unit, which is essentially the distance between Earth and the Sun, then of course we know from our own experience that it takes 365 days for the object to turn once around the central mass. So one turn per year means one turn per 3 times 10 to the 7 seconds. That means a frequency of less than 10 to the minus 7 hertz. So if you want to go to higher frequencies in this range above 1 hertz, you have to go to extremely small radii, 1,000,000 times smaller than the radius of the Earth orbit, which is something like in the order of 150 kilometers, say 100 miles. That you have. Now, of course, the Sun is much larger than that, so with the Sun it will never work. but as we will see, there are objects, compact objects, that are very heavy as the Sun, but much smaller, and for which this actually could be working. The red curves, the red lines here, tell you the amplitude of the gravitational waves emitted by this system as seen from a certain distance. So 1 kiloparsec, which a parsec is a distance measure used by astronomers in about 3 light years. 1 kiloparsec is 3,000 light years, is basically in our galactic neighborhood. So if the object is in our galactic neighborhood and you want to have, say, 1 hertz frequency, then you have to have a binary system of radius 10 to the minus 5 astronomical units. But at 10 kiloparsec, of course, the signal becomes 10 times smaller. At 1 megaparsec, which is, say, the distance to Andromeda or something like that, the signal becomes even smaller, 1,000 times smaller, and 10 to megaparsec is barely enough to reach the Virgo cluster. So you see that the binary systems that we are talking about give you gravitational wave signals which are in the regime of about 10 to the minus 23, even if you allow for very low frequencies. But there is some evidence, nevertheless, for gravitational waves. It's indirect evidence, and it comes from observations which started with the discovery of a very special object known as the binary pulsar PSR 1913 plus 16, discovered by Hulse and Taylor in 1975. And basically, this system consists of 2 neutron stars. A neutron star is a star, say, of a mass a little bit larger than the Sun, that has collapsed to a density where it's basically made only of nuclear material. So the density of a neutron star is actually larger than that of an ordinary nucleus, and it can pack the mass of a star like the Sun in an object which is about 10 miles in diameter. And those objects have been discovered in the 1960s, and many of them have strong magnetic fields, as a result of which they are able to make very strong pulses of radio signals that periodically, when the neutron star rotates, sweep over the Earth, and we see a periodic signal, and that's why they're called pulsars. And in Hulse and Taylor in 1975 discovered a pulsar which was part of a binary system where the other star was also a neutron star. So these 2 neutron stars are heavy, 1.4 solar masses about, and are moving at a radius of about 4 million kilometers, which is about 1/100th of the radius of the Earth's orbit. Their typical orbital period is 7 hours, 7.5 hours. So the frequency you would expect from this binary pulsars in gravitational waves would be about a millihertz. Now this binary pulsar, because of these very regular radio pulses that it's emitting, you can actually track the motion of the 2 neutron stars with respect to each other by just measuring the Doppler shift of these pulses of radio waves. Periodically, one neutron star will move away from us, and it will be shifted to the red, and when it moves back to in our direction, it will be shifted to the blue. This way we can keep track of the motion of this neutron star around the other neutron star.
And what's the source of that radiation?
It's extremely strong magnetic fields, and there will free electrons and so on, which emit synchrotron radiation. And this binary pulsar, therefore, can be used as a model to study the motion of compact objects in very strong gravitational interaction, at least much stronger than, for example, the Sun and Mercury. And one of the effects that is clearly observed in this system is the shift of the periastron. So the point of closest approach between the two neutron stars. For Mercury, we know that this point of closest approach of the planet Mercury with respect to the Sun changes by 43 seconds of arc every century. For this system, it changes by 4 degrees every turn. So it's really easy to measure, and it's beautiful confirmation of general relativity. Except that there is a small deviation. This actually, it turns out that this periastron, this point of closest approach, actually shifts a little bit more than, or a little bit less, I should say, than you expect on the basis of pure geodesic motion in general relativity. But that can be explained because the system is emitting gravitational waves, and therefore the neutron star loses energy. And it slowly creeps, the two stars slowly creep towards each other. And that changes the periastron. And if you take that into account, it turns out that the observations and the theoretical calculations are in beautiful agreement with each other.
So there's no loss of energy from the radio waves?
Well, very little compared to in fact, in this time, compared to the gravitational waves. Yes, because basically the energy from the synchrotron radiation is caused by the electrons, which are moving, say, as free particles around the neutron star, but not from the motion of the neutron star itself. So this is an indirect confirmation that this system here is actually emitting gravitational waves. Unfortunately, the frequency range is in the millihertz, 1/10 of a millihertz, and that's not possible to measure with any terrestrial object, because any object that you put on the surface of the Earth will have to, will be subject to seismic motions, and seismic motions become very large compared to any gravitational wave effects when you go below 10 hertz. So basically there's a cutoff that gravitational wave detectors on Earth can detect. Namely, gravitational waves of below 10 hertz will not be observable by terrestrial detectors. Here you see actually a calculation of the orbit, the change in the orbit, the size of the orbit of the two neutron stars. The outer curve here represents the present orbit. This is the center of gravity of the system, and this orbit is slowly getting smaller and smaller, and in 250 million years, which means one turn of our galaxy, there will be this orbit will be deformed so that the stars will be less than 1 million kilometers apart. In fact, this means that the orbits are changing by about a few millimeters per year, and that's what we actually measure here. So it's really incredible.
If we wait long enough, the gravitational waves will become stronger.
Yes, absolutely. Yeah, definitely.
I'm waiting.
You need to have some time to wait, but fortunately there are more systems. This is the first system detected, but since this system was found, at least 20 more such systems have been detected, and in all cases it has been checked that this gravitational wave emission is reproduced. So we're pretty confident that these systems do emit gravitational waves, but unfortunately we haven't the technology yet to measure it. Okay, now the other prediction of general relativity, as I mentioned, is black holes. What's a black hole? Well, because space and time can be curved by masses, actually if you put enough mass within a very small volume, the curvature can become extremely large. And general relativity predicts that if you put a mass inside a volume with a radius given by this quantity here, 2 times Newton's constant times the mass divided by velocity of light squared, which is called the Schwarzschild radius, then actually it will form what is called a horizon. At the radius of this, at this structured radius, there is an event horizon. Anything which falls through this horizon is unable to return to the outside, and it also cannot send any signals back to the outside. So it's forever lost from communication with the rest of the universe, and we don't know what happens inside. So that's what's called a black hole. By some accident, at least as far as we know, it's just an accident. If you take a Newtonian theory of gravity and you calculate at what distance for a given mass m the escape velocity becomes equal to the velocity of light, turns out to be the same quantity, the Schwarzschild radius. So you can also give it, say, a Newtonian interpretation. Newtonian interpretation would be that that if your object becomes that compact, the escape velocity becomes larger than the velocity of light, so light could never leave the object. But general relativity explains it in terms of curvature, and that, of course, is the much better explanation. Now, also for black holes, there is indirect evidence that they really do exist. And one piece of evidence you see here, this is a plot of the motion of a number of stars, about 20 stars, very close to the center of our galaxy. These stars have been followed between 1995 and the year 2011. And you see the orbits of these stars plotted as far as they have been measured. And it's absolutely clear that somewhere here in this small ellipse, which is the motion of the star closest to the center of the galaxy, there is some mass which causes these stars to orbit in Keplerian orbits, ellipses, basically. In fact, rotating ellipses, because it's general relativity. And if you calculate the size of the mass that must be concentrated in this little point here, it amounts to almost 4 million solar masses. So there are 4 million solar masses which are totally invisible, concentrated here in a little area, little volume in the center of our galaxy, which is much smaller than the size of any stellar orbit. So that is why we believe that there is a black hole there, hidden in the center of our galaxy, and that these stars are all orbiting this black hole. And well, our theory, just roughly developed, tells us that these systems should be emitting gravitational waves. You see that the periods here that we are talking about are 10, 15, 20 years or more. So the frequencies are extremely low, even much lower than that of the binary pulsar.
Isn't there some kind of a pulse of gravitational wave when the thing comes very close and it's accelerating rapidly? It's true that, of course, then the acceleration is larger, and the intensity of the gravitational wave power varies during the orbits, but that is still not large enough, that effect, to make we know when to look.
Yeah, yes,
Which
sure.
should help.
But let me...
Can I go back to the
Yeah.
slide? So the,
Oh, sorry.
yeah. So that the 5045 that is going up and slightly to the right, that seems does not affect.
This one.
Oh no, not that one.
That one.
Yeah, that one.
Yeah, well...
That seems like that's just going.
Yeah, it's difficult because, of course, this is a two-dimensional projection of a three-dimensional motion.
Okay.
So that makes it hard to interpret. It could be that it is quite far away and that the curvature of its orbit is very small. But I really can't say more about it. I don't know enough. So here you see something else, namely that by now astronomers have found that in almost all major galaxies, which means galaxies of the size of our own galaxy or larger, such mega heavy black holes are hidden in the center. In fact, the one in the center of our galaxy, which is between 3 and 4 million solar masses, turns out to be a relatively small one. In some galaxies, there are black holes hidden which are 200 million or even 2 billion solar masses. So it's now generally agreed, I think, by astronomers that
somewhere in the evolution of galaxies, these large black holes are formed, probably in the early stages of galaxy formation. The density of stars in the center is very large, and they start to collide. Some of them explode as supernovas and may collapse to a stellar mass black hole, and then eat the stars in their neighborhood. And by merging, these black holes can become larger and larger. And by now, they seem to be the central object in most major galaxies. So these very heavy black holes seem to be very abundant also, because we know that there are at least 800 billion galaxies visible in the visible part of our universe. So one of the things that one can do is now try to see if we can learn more about black holes by studying the gravitational wave signals of objects that move in the background of these black holes. Then basically from the gravitational wave signals you should be able to map out the properties of the space-time around the black hole and confirm or test general relativity in that way. So here's the idea: you have a black hole and you have another mass, say a neutron star or something like that, a compact object which with respect to this black hole can be regarded as a point particle and is moving on a geodesic, in this case just the easiest case, just a circle around the black hole, and is emitting gravitational waves. And of course we would like to know the size and amplitude of these waves. Now the motion of this compact object around the black hole is characterized by two constants of motion. That's easy. There is energy, which is conserved if you neglect for the moment gravitational radiation. And there is angular momentum, which is conserved. Now angular momentum means that this object moves in a plane, because angular momentum has a direction and a magnitude. If the direction is constant, it means that the motion is always perpendicular to this constant direction, and means it moving in a plane. So this object is moving in a plane, and then the only freedom that you still have is that this object can move further away from the black hole and closer to the black hole, but the conservation of angular momentum, the component along the z-axis here, tells you that, like in Kepler's law, Kepler's second law, that if the object moves further away, it will start to move slower, and if it moves closer to the black hole, it's moving faster. That's angular momentum conservation. And that's expressed by this equation here: the radial velocity squared plus this function of the radius together is a constant of motion defined by the energy of the object. And this quantity you can think of as an effective potential. It has been plotted here for various values of the angular momentum, and you see there are two regimes. One regime, when the angular momentum is large, there are three terms here. There is four terms. There is a constant term. There is a term which goes like 1 over r, a term which goes like 1 over r squared, but also a term which goes like the product 1 over r cubed. And this 1 over r cubed, of course, is the dominant term for very small r. So always the potential will fall steeply to zero when you go to small r, you go close to the horizon. But for the large r behavior, or the intermediate r behavior, depends on the size of the angular momentum. And if the angular momentum is larger than 12 times m squared c squared, the Schwarzschild radius squared, then actually it turns out that there is a minimum and a maximum in this potential, which means that there are two places where you can have circular orbit, because both at the minimum and the maximum the RDT can be zero, and you move at constant radius. Now, of course, if you are at the maximum, this is an unstable motion, because a very small perturbation to the left will make the object fall into the horizon, the black hole. But the other one here, this minimum, is a stable circular orbit. However, if the angular momentum becomes small, then this contribution becomes relatively small, and then in fact these two stable points in the potential disappear. And actually it means that if you are getting close to the black hole and you don't have enough velocity, the angular momentum is not large enough, then you cannot maintain your circular motion around the black hole. You start to fall into the black hole, right? That's kind of obvious from this picture. And in that case, there is no stable circular orbit. But there is precisely one intermediate case where these two stable points of the potential coincide, and there is actually a flexion point here where the potential does have an extremum. It's temporarily stable. That is called the innermost circular stable orbit, the ISCO. So the black holes are distinguished from ordinary Newtonian binary systems in the fact that there exists this innermost stable orbit. In fact, this innermost stable orbit takes place when the radius of the orbit is 6 times the Schwarzschild radius. And then that means so that as soon as you get inside this smallest circular orbit, there is no way that you can keep circling around the black hole. Basically, you would have to have the test mass would have to have a speed larger than the speed of light, which is impossible. So that's why there is no stable orbit inside this ISCO, and nevertheless, this ISCO is well outside the horizon.
But presumably, that's way inside the Roche limit of something like that for any ordinary type of object.
For so sure, for in the sun the Schwarzschild radius is 3 kilometers and the sun has 1 million kilometers diameter or something like that. So this motion, of course, for ordinary stars will never be relevant.
I mean, even ordinary stars will have a Roche limit associated with the tidal forces near the black hole, and that should be way further out, much further out than this particular most circular.
What is a Roche
limit?
Roche limit?
Where the tidal forces rips the orbiting object.
Oh no, not for neutron stars. I
Not for
think.
neutron stars?
No. They are very, very stable. They're almost black holes because see, their radius is almost only twice their Schwarzschild radius.
Okay.
Listen. There's nothing coming. So let's try again. Maybe there is. Okay. Well, I'll come back to that. Here, just to show that I have been working on this this problem. Here you see the change in the orbit of the circulating mass as a function of distance for an eccentric orbit with eccentricity point 15 that we have calculated, and of course it starts out with frequencies which are large or are small, periods which are large compared to this ISCO, and the ISCO is the endpoint of evolution. After that the thing has to start moving towards the horizon and fall into the black hole, and you can see that the eccentricity effect of the orbit is decreasing when you get closer and closer to the ISCO. So even if you start out with an orbit which is eccentric, when you get closer to the black hole, the loss of gravitational radiation, which takes with it also angular momentum, will make the orbit more and more circular. Here you see, okay, this one you could hear. What happens if you have two masses of neutron star size, compact objects, stellar mass compact objects, which are in bound states like the binary pulsar. When they reach the end of their life, also there the speed, the frequency starts to increase and the amplitude starts to increase. So you see this kind of signal which first for a very long time is more or less stable at the fixed frequency, but once the final stage of the motion of the coalescence is reached, both the amplitude and the frequency will go up, and you hear the signal. The signal that you heard was actually the true frequency of this gravitational wave. So it's in the kilohertz range. That's why it's audible. Yes, if it would be a sound wave, you would hear it. And the interesting thing is, of course, as you'll see, that because it's so non-linear process, when such a coalescence takes place, from just observing the relative change of the amplitude as a function of the relative change of the frequency, you know basically how far the system is away. You don't need to know anything, because the change in frequency and the change in amplitude are unique for a system of given masses. And that means that the amplitude, you know the absolute value of the amplitude. If you observe this signal, then from the apparent amplitude, you can reconstruct the distance to this binary system. You don't need to take any recourse to other measures of this in the universe, like normally you have to do, that you have to use variable stars and supernovae and so on to calibrate distance measurements in the universe. From observing these objects in gravitational waves, you can directly determine the distance to the object, and therefore you have an independent and much better measurement, for example, of the Hubble parameter, which describes the expansion of the universe.
Do we have detectors that are well enough calibrated to detect the absolute power that
the existing gravitational wave detectors, LIGO here in the US and Virgo in Italy, they can measure this gravitational wave if it happens in a galaxy not further away than the Virgo cluster. So that means, say, 10 megaparsec away from us. That still means it's very, you have seen that it takes a long time for these systems to coalesce, and this last phase lasts only about 15 minutes or so. So you have to be very lucky to catch such an event, or you have to have such a sensitive detector that you can measure many more galaxies in your field of vision, of detection, so to speak.
And you'd still have some sort of inclination in uncertainty as well, is that right, in terms of the relation between the observed strength and the...
Yeah, so that, of course, this is, well, I'll come to that now. So how do you measure gravitational waves? Well, somehow you have to extract energy from the gravitational wave, or you have to lose energy to the gravitational wave. If you have a measuring apparatus, the state, the amount of energy in your measuring apparatus has to change as a sign of the fact that you have had an interaction with the gravitational wave. And the simplest and earliest attempt to measure gravitational waves were with mechanical detectors. Basically, you can think of them as a sophisticated form of this spring here. If you have a spring with two masses and a gravitational wave passes by, then this string is compressed or pulled apart, and by the time the gravitational wave leaves, the spring has changed. The two masses in the spring have changed their distance, and the string starts to oscillate. It takes energy from the gravitational wave and puts it into an oscillation of these masses. And if you measure this oscillation, you have detected the gravitational wave, even though the gravitational wave may have passed a long time already. So here the attempt was to create vibrating objects which were actually isolated from the environment extremely well, later also nowadays operating at liquid helium temperatures to make them really the mechanical noise very low and so on. And at present, still a few of these mechanical gravitational wave detectors are in operation.
What year is that?
Weber started around 1960, 59 or 60, and he reached sensitivity age of about 10 to the minus 16, he claimed. Nowadays, these detectors have been improved, and they are capable of measuring amplitude of 10 to the minus 20, roughly. But
and they're
given
comparable size to what you guys were.
Yeah, they're the best. The biggest improvement. There are two big improvements. One is that they are cooled to liquid helium temperatures, and the second is that the motion detectors nowadays consist of superconducting devices with Josephson junctions, and they are much better than the piezoelectric type of motion detectors he used. But these detectors have now been overtaken by the laser interferometers, LIGO and Virgo, and the Japanese instrument, the German instrument GL600. Basically, they consist of two very long arms of a Michelson interferometer. In the case of LIGO, I think it's 4 kilometers. In Virgo, in PISA, they are 3 kilometer arm lengths. And the change, we have seen that the gravitational wave, when it makes one arm shorter, the other arm gets longer, and vice versa. So you can actually detect a phase shift between the light coming from one arm and the light coming from the other arm, and in that way reconstruct the passage of a gravitational wave. Now these instruments now claim sensitivities of H about 10 to the minus 22, so they are 100 times better than the mechanical detectors. But there are also other schemes. One scheme is to put a number of satellites in orbit around the Sun. This is called the ELISA project, and is a plan of the European Space Agency, unfortunately still with no definite time date. But the idea is that there will be 3 satellites in orbit around the Sun, and they will track each other's distances using laser signals. And from the relative motion of the test masses in each of these satellites, they will be able to detect the passage of gravitational waves. And the main advantage of this scheme is that the arm length is extremely long. You can make arm lengths of 1,000,000 miles or more. That means that the frequencies that you can detect with this detector are in the millihertz range, where the binary neutron stars are emitting gravitational waves. So you are sensitive to sources which you would never be able to see from the surface of the Earth. There's also an attempt by astronomers collaborating in something called a pulsar timing array to track the position of a number of neutron stars, pulsars, in our solar galactic neighborhood with very high precision, measuring all these Doppler shifts. And from the relative motion of the pulsars with respect to the Earth, determine the passage of a gravitational wave. So basically they use the Earth and these pulsars as test masses of a detector, and the distance is tracked by measuring the Doppler shifts in the pulsar signals.
So on the pulsar timing, there's also noise on the pulsar period that's
Yes.
associated with just random gravitational waves. Is
Yes,
that right?
well, that is in fact the lower the frequency that you actually are sensitive to, the more background sources there will be. For example, in addition to all these binary neutron stars in the galaxy, there is a huge number of binary white dwarf stars, or star systems with one white dwarf and one ordinary star, and they are also emitting gravitational waves in millihertz or microhertz range, and they will create an basically stochastic background from which you have to try to extract the signals.
Yeah, so that's exactly my question. Is anybody be able to extract that stochastic background from instrumental noise and making the pulsar?
Well, it's not the instrumental noise, I think.
For the pulsar timing, I mean.
Oh, and for the pulsar timing. Well, that just depends on how long you can. These telescope radio telescope arrays can, of course, measure for very long times, years, if necessary, keeping the phase coherence.
They've been going for 10 years or so doing this project.
Yeah, no, that is why there's a huge competition. There's a huge competition between different observers, the people building terrestrial gravitational wave antennas, the pulsar timing arrays, the space proposals, and nobody knows who will win, what signal will be observed first. So let me, how much time do I have, actually?
5 minutes?
5 minutes? Okay. So let me come to my last topic in this context, which is cosmology. We know that the universe is expanding, has been expanding for 13.7 billion years. And we know that from the observation of variable stars, the Cepheid variable stars in Andromeda, first observed by Hubble, than in other galaxies, and it turned out that all these galaxies were receding from our local neighborhood, and that the velocity increases with the distance. So that points to the fact that the universe as a whole is expanding. There's the well-known story that if you go back far enough in time, there was a period in which hydrogen was not stable. Electrons and protons were basically free particles. There was a plasma of very hot charged particles in which light could not propagate because it was scattered all the time. So there was basically acting like a mirror. And then when the temperature dropped below about 3000 Kelvin, suddenly the hydrogen in the universe, well, electrons and protons could combine and hydrogen became stable. And then from that moment on, light could travel through the universe without being scattered all the time. And that light is still around. It's the cosmic microwave background. And first COBE, later WMAP, and now the Planck mission has made beautiful pictures of the light distribution all over the sky, subtracting the background from our own galaxy, and found that the temperature of this radiation is extremely constant all over the sky. The temperature of this radiation in present day is 2.73 Kelvin, and the variations that are represented by the different colors here, red and blue, they represent variations in the temperature of the radiation of less than 10 to the minus 4. 1 part in 10 to the minus 4. So the temperature all over the sky is very uniform, and that points to the fact that this cosmic microwave background actually dates from this recombination era that followed a few 100,000 years after what we conventionally regard as the Big Bang, the start of the evolution of our universe. Now, the fluctuations, you can plot the size, the distribution of fluctuation of various size in this picture, and you get this graph here, which shows you that the largest size fluctuations are, roughly speaking, 1 degree here, and that tells you something about the distribution, the fluctuation in the distribution of matter in the early universe. It's one of the hints that in addition to baryonic matter, there is a lot of dark matter in the universe, because otherwise you cannot explain the different peaks in this distribution. But what now actually people are hunting for is not just the density fluctuations, but there could also be what is known as tensor modes in this cosmic microwave background, called E and B modes. And here you see basically what is meant. The E modes are ones that have zero curl but non-zero divergence, and the B modes are polarization patterns which have a non-zero curl but a zero divergence. And people have started to hunt for these tensor modes because they are possible signs of gravitational waves that date back all the way to the Big Bang itself. So the period before the recombination of protons and electrons to form neutral hydrogen. And so observing gravitational waves basically means you have a window on the universe in the first 300,000 years of its existence. So far, these gravitational wave signals in the cosmic microwave background have not been observed, but tensor modes have been observed by now by an experiment called the South Pole Telescope. Here you see the measurements and the statistical errors, and you see that they definitely do show a signal, a non-zero signal. This signal actually is believed to come from gravitational lensing effect. So there's matter in the universe, and when the light from the cosmic microwave background passes, say, a cluster of galaxies, then the light is bent by the gravitational effect of this cluster of galaxies, and that also creates tensor modes in this cosmic microwave background, and they have been observed. The primordial modes, which come from gravitational waves, so far have not been detected, but who knows, someday Planck or one of its successors will detect these modes, and we will have information about the universe which seemed impossible to reach until now. So there are many ways that gravitational waves can give us new insights and new information about the state of, about the physics of space and time, about the geometry of black holes, but also about the Big Bang and the early universe. So there are big rewards when finally we will be able to observe for the first time gravitational waves. What is completely unclear is at the moment how long it will take and what wavelengths in with what frequency range we will first see gravitational waves, whether it will be very, very low gravitational frequency gravitational waves from the Big Bang, whether it will be microhertz waves measured by pulsar timing arrays, or whether it will be, say, acoustic frequency waves measured by terrestrial detectors from coalescing binaries, gamma ray bursts, or supernovae. And the latest development is that now both LIGO and Virgo, the interferometers in the US and in Italy, they are upgrading their optics in such a way that they hope they will become 10 times more sensitive than they are now. And 10 times more sensitive means they can look 10 times further into the universe, but that means that the volume that they can observe of the universe becomes 1,000 times larger, so you have 1,000 times more sources. If you would have a chance of 1 in 10 to observe a source today, they will have a chance of 1,000 in 10 to observe a source maybe after the upgrade. And so they are hopeful that they will be able to detect these gravitational waves from neutron star binaries maybe in the next 5 to 10 years. So to conclude, here is an overview of the gravitational wave spectrum. It covers an enormous range of frequencies, from 10 to the minus 17 for waves that originate in the Big Bang to say kilohertz acoustic waves, frequency waves coming from binary neutron stars and rotating neutron stars, which I haven't even mentioned. And here you also see the different instruments and the different methods that are being used to try to hunt for these gravitational waves, from the terrestrial interferometers all the way to the cosmic microwave background for the lowest frequencies. And anybody can place his bets on who will be the first to reach the ultimate goal. But let's hope it will not be too long before we actually able to do this new kind of physics and astronomy. Thank you.
I wonder, does the stiffness of the Earth have anything to do with the sensitivity of the terrestrial interferometers?
Well, the crust, yes, in some sense, because the spectrum of seismic fluctuations, of course, is determined.
I'm thinking from just the response of the detectors.
No, because the of course, what say in the ideal case, what you would like is the mirrors in the interferometers to be in free fall, because then they would really be define local inertial frames, each of them, and you could measure the change in distance between these two local inertial frames. But that, of course, is impossible, because they would the Earth's gravitational field would make them fall. So you have to hang them in some way. But they're very subtle constructions using very fine quartz wires and many stages of isolation, vibration isolation. So there's something like 400 dB vibration isolation between the surface of the Earth and these objects. But nevertheless, the whole thing moves at frequencies below 10 Hertz, basically, and those you cannot avoid. There is, unfortunately, for gravity, not something like negative charge, which you can use to screen and build a cage of Faraday. We cannot screen gravitational fields that we don't want to see.
So is the solar wind a significant background for LISA?
The solar wind, no, it's not, because the LISA, basically the test masses are little blocks of gold which are hidden inside, we are free floating inside the satellite. So the satellite is basically just a kind of screen cover for to protect the test masses from being hit by all kinds of things like dust or meteorites or solar flares or whatever. And in order, of course, to make sure that these test masses inside will stay in free float, it's actually the shell of the satellite which will be moved by micro rockets, which can be commanded from Earth, and so they can be moved so that the actual masses, test masses, stay free of contact with the rest of the satellite.
With the terrestrial interferometers with lines at 90 degrees, are they sensitive isotropically or in some direction?
No, they are absolutely direction sensitive, or because basically the gravitational waves, of course, if they come from the zenith angle, then there's maximal sensitivity. You are in the same plane as the plane of polarization of the wave. But if the wave comes at an angle, you see only part of the polarization and part of the signal. In fact, this is a personal story. The first time I got involved in gravitational waves physics there was a plan in Italy and in the Netherlands to build a spherical mechanical gravitational wave detector. Because if you make a sphere, it is actually, its lowest vibration mode is the quadrupole mode, this squeezing. And you are sensitive to all polarizations of the gravitational wave, whatever direction it comes from. So you would also always have maximal sensitivity. But unfortunately, the plan was never realized because of financial difficulties.
Again, for the terrestrial interferometer, can a wave come through the Earth?
Like neutrinos, you mean?
Yeah.
Yeah. Basically, the wave doesn't care where it comes from because it's not scattered by the Earth. It passes right through the Earth, and even if it loses, say, 1/1,000,000% of its energy to the Earth, doesn't matter.
So, can these gravitational waves redshift? And if so, what implications does that have on constraining cosmological parameters?
Yeah, no, that is true. Certainly, the expansion of the universe will make the gravitational waves being redshifted if they are far away. So, again, if you can do a sufficiently careful analysis of all the nonlinear effects in this this signal for coalescence, you can actually also measure that redshift from the same signal. But you need not only the amplitude and the frequency, not only the rate of change, but also the rate of change, so to speak. And then you can also take into account such effects.
More questions?
So, for the terrestrial interferometers that have the sensitivity they have now, how many sources, or have they estimated the number of sources that could fit into that frequency?
Oh yes, absolutely. In fact, if they hadn't, they would never have gotten funding. So at present, they claim that all of the instruments, even the mechanical detectors, if there would be a supernova in our own galaxy, every detector would see it. No problem, because its amplitudes would all be 10 to the minus 20 or larger. So, but then that of course is an event that happens only twice a century on average, or something like that. So that's not something you can bet on. Then the binary neutron stars, they have actually estimated, I think they have a chance of, say, to see 1/2 such an object every year, so one object in 2 years. But that has, of course, statistical fluctuation. So if you run your detector for 2 years, you don't see anything, you don't know anything. But of course, if you now increase the volume of space that you can monitor by a factor 1,000, then the number of sources will also go up by a factor 1,000. And that means instead of seeing one every 2 years, you will see 1,000 every 2 years. And then you should be pretty sure that you can see. That's at least what they claim. I can't verify the claim, but that's what they tell us.
So what fraction of time are these detectors actually listening?
Oh, when they are, by now they are doing the upgrade I was talking about. But they have been operational for 2 years or something like that. At some point it doesn't help to operate much longer, because your statistics doesn't increase much better by, say, if you operate them for a factor 2 longer or so.
More questions? Is it a 100% duty cycle?
Sorry?
The duty cycle, is it 100% for everything? Or is it like
Always
when
on.
it's on? It's
Yeah. Well, yes. No, it's not that there is dead time or anything like that.
Okay, let's thank the speaker. Jan-Willem will be still around tomorrow, and if you will still discuss
It was a bit difficult to estimate at what level to give the talk, but okay, thank you.
I'll catch you. We'll see how bad things are.
I've been telling you. The idea was that they would register, but they forgot.
They register $25 registration.
Yeah, but it includes all the meals for the week.
So it's approved?
Huh?
What?
So I'm just that you approve it already now?
Proving what? $25?
Yeah, I mean, whatever. So I've been telling everybody to just come. I have the whole thing. Hi.
Hi.
Carl Sandick. Carl Sandick.
Hi, Jan van Holten. Ah, okay. Nice.
What is the dinner for?
One is that we are going to Bristol.
Yeah, at 6. Meet here at 6 or meet there at 6?
We'll be there.
You'll be there at 6?
Yes.